Now we will move on to inclusion-exclusion. And as I said before, we have covered inclusion-exclusion already, but now we are going to be talking about a more general version. Well, let's recall what we know about it so far. Inclusion-exclusion for two sets tells us that the cardinality of A union B is equal to the cardinality of A plus the cardinality of B minus the cardinality of A intersect B. And what we're going to do is generalize this to more than two sets. So let's look at how we got this formula, or sort of what is the intuition behind this formula. So the idea is that let's draw ourselves a nice little Venn diagram. Here's A and here's B. And the idea is that we want to count the cardinality of A union B. So we start by taking the cardinality of A, and that counts this area and this area. And then we add the cardinality of B, and that counts this area and this area. And we see that this region we have counted exactly once, and this region we have counted exactly once, but this region we have counted twice. So we have double counted those parts, and we need to basically subtract cardinality of A intersect B, because that's this part, and that gives us the correct count by removing the double counting. So the point is that this part double counts A intersect B, and so by removing it, we get the correct count. So let's go through the same process for three sets now and see what we end up with. So let's draw ourselves another little Venn diagram. Let's see, where should we put it? Let's put it here. All right, so here is A, and here is B, here is C. Okay, and let's start off. We want to compute A union B union C, so this sort of whole region. And we can start by saying that it is the cardinality of A plus the cardinality of B plus the cardinality of C. Here's our starting point. So when we say the cardinality of A, we count this region. Let me use maybe some dots. This region, this region, this region, and this region. So those together make up A. And then when we add the cardinality of B, we count this region, this region, this region, and this region. And then when we count the cardinality of C, we get this region, this region, this region, and this region. So we can see that we have got some double counting problems. So for starters, we have overcounted all these intersections, right? So let's start by subtracting those off. So minus, right. So this has double counted the intersections. So let's subtract cardinality of A intersect B minus A intersect C minus B intersect C. And so what does that do? When we subtract A intersect B, namely this region, let's erase one of the dots from each of those spots. So there's one, there's another. Good, good. When we do A intersect C, which is this region, we get rid of a dot from each of those, like so, and like so. And similarly, when we subtract B intersect C, which is this region, let's get rid of it off from each of those, like so, and like so. So now we see that these sort of regions are correctly counted. We've got 1 dot in each of them. But this region, in the center, we have subtracted it off. So, we added it 3 times in the beginning, and then we subtracted it 3 times in our second step. So now we have counted it 0 times. So now we need to add that thing back in. So in the first step, we overcounted the intersections. In the second step, then, we undercounted the triple intersections. So we add back the triple intersections. That puts dot in there. And now we see we have the correct count, counting each region exactly once. So this is the more general form of the principle of inclusion-exclusion. Let's write down the formula now for an arbitrary number of sets. So for n different sets, we have a1 union through an. How do we compute this? Well, again, we start with the sum of the cardinality of each set. So I is going to range between 1 and n. And then so let's say we include sets and then subtract the intersections. AI intersect AJ. So exclude intersections. I'm going to write these sorts of things just to give some idea of why this is called inclusion-exclusion. And what do the indices do in this sum? Well, we want to take each intersection exactly once. So let's say I is strictly less than j. That will ensure that, first of all, they're different, and second of all, we don't count them twice by doing both ways. And then these should just go between 1 and n. And then we want to add back the triple intersections. So include triple intersections. And in this case, we want 1 less than or equal to I, less than j, less than k, less than or equal to n. And so on and so forth, until finally we get to plus minus 1 to the n times the n-fold intersection of all the sets. So you see before you the full principle of inclusion-exclusion. Very good. So let's give a quick sketch of a proof of this thing. The example we gave of 2 sets and 3 sets is basically a good illustration of why this is true. But let's go ahead and write it down precisely. So I wrote this kind of big. It's going to be a struggle to get it all on the screen. But let's just zoom out a little bit. No problem. All right, proof sketch. So I'm going to be a little bit, quick flying through this, but this is basically the idea of how to prove this. Suppose some element x is contained in exactly R of our sets. So every x is contained in some number of sets. So this is just saying let x be any element, and let R be the number of sets that it's contained in. And we want to show that it's counted once exactly in this big formula. So the first term, so that's this guy. How many times do we count x in this term? Well, if it's included in R of the sets, it is counted R times. So it counts x, R equals R choose 1 times. Second term counts x, R choose 2 times. Because that's this term, or let me say negative R choose 2. Because it's got a big ol' negative sign in front of it. And why is it R choose 2? It's because wherever our element x appears in this sum, it is choosing 2 out of the R sets that it is contained in. So R choose 2 is the number of ways to do that. And etc. So the total is R choose 1 minus R choose 2 up to minus 1 to the R minus 1 R choose R. And this is equal to 1 because we have some binomial identity using our, one of our clever binomial tricks. We expand 1 minus 1 to the R, and what we get is 1 minus R choose 1 plus R choose 2 plus minus 1 to the R choose R. And this is just 1 minus the number of times we've counted our thing. So 1 minus our count. And since that's equal to 0, it shows that this thing must be equal to 1. Very good.